Okay, so this time we'll finish up chapter 21. So here we'll talk about the charges quantized, 电荷量子化. Okay. Of course, here we won't talk about too much about the quantum mechanics stuff. You only need to know electrons are 1, 2, 3, 4, 5, something, so on and so forth. Of course, it can have negative charge. So generally, you can write a Q to be a multiple of E, and N is the multiple. So N can be plus or minus 1, plus or minus 2, plus or minus 3, so on and so forth. It can N can only be integers. Yeah. But of course, what is E? E is the elementary charge. Okay. 单位电荷，或者是基本电荷。Which means an electron has this charge amount, of course, in the negative side. Of course, this E is defined to be a positive number, so E to be 1.602 times 10 to minus 19. Yeah, of course, when we do calculation, I usually drop out the O2. I just use 1.6 times 10 to minus 19 Coulomb, which is sufficient usually. Okay, so this is quite easy. Okay, I suppose you should have known it in high school chemistry. Okay, so on the bottom we have a table. So it says in high school chemistry we know there are 3 types of fundamental particle. Yeah, like electron, proton, and neutron. 电子、质子、中子. Okay, so for the electron, it has a negative E of charge, and then for the proton, it have a plus E of charge, and then for the neutron, it is electrically neutral, so it's called neutron. So nothing special. Okay, so here, it says when the physics quantity such as a charge can have only discrete values rather than continuous value. Okay, rather than continuous value. Usually we will consider the values to be continuous, just like the mass of everyone. Maybe for me, maybe 70 something. You can imagine it is 70 point something. Okay, it can be a fractional number. Yeah. So it looks like a continuous number. So rather than discrete value, we will not consider the mass of us can only be just like 70 kilogram, 71 kilogram. No other values in between. It's not. It doesn't make sense. Okay, but for the charge, okay, if there are lots of charges, then it feels like it's continuous. But when we really need to separate into the fundamental charges, it cannot. So the smallest amount can only be 1.6 times 10 to the minus 19. You cannot further separate into even smaller charge. So when you go to a very small scale, then you will see what is discrete value. Why the charge is discretized or quantized. Okay, rather than any value, we say that the quantity is quantized. Quantized. So it's possible, for example, to find a particle that has no charge at all. No charge, n equals 0 is also okay. No charge at all, or a charge of plus 10e, minus 6e, but not a particle with a charge, say 3.57e. This is not okay. Okay, so for checkpoint 4, it says initially SPA has a charge of minus 50e. and sphere B has a charge of plus 20e. The sphere are made of conducting material and are identical in size. So if the sphere then touch, what is the resulting charge on sphere A? On sphere A. So the condition identical in size is important because it means that after the two spheres touch each other, the total amount of charge will equally separate for the two spheres. Okay, so which means that when we need to solve this simple checkpoint, so first of all, we need to know what is the total amount of charge. So here there are for sphere A. For sphere A, it has negative 50e, and then for sphere B, it has plus 20e. Okay, so then we touch each other. Okay, touch each other, and then the total amount of charge will equally separate the two spheres. So here we have a total amount of charge to be negative 50 plus 20, which is 30e. Sorry, negative 30. Negative 30e. To be negative 30e. Okay, and then this is separate for the two spheres, which means that each of the sphere will have a negative 30 over 2, which is a negative 15e. So this is the answer. Negative 15e. Okay, so this is just a simple checkpoint. Okay, so next we will try to talk about the a sample problem. Okay, a sample problem. Okay, so actually this sample problem is quite simple. You just need to substitute the value into the Coulomb's law. So if you realize it is very stupid. But actually, there are some physics story behind. So let's see what it tells us. Okay, so it says, so it says the nucleus of an iron atom, 铁原子, has a radius of about 4 times 10 to minus 15 meter and contains 26 protons. What is the magnitude of the repulsive electrostatic force between two of the protons that are separated by this radius? Okay, of course it is a nucleus. Okay, of course outside there will be some electron. Of course it's not very true, but at least it is true for high school chemistry level. Okay, so we know that this is the nucleus, and we know that there are some proton plus and then neutron without any charge in the nucleus. Okay, so yeah, there are some proton and some neutron packed inside the nucleus, and as you know, the proton and neutron cannot really move. It can just oxidate in that area. Okay, so so it tells you that this is the radius, and then it just asks you to estimate. For example, there are two protons of this proton and that proton with the distance out. Not necessarily all the distance between any two protons to be out, but yeah, just an estimation. At least the radius is out. So yeah, you expect some of the protons may have the distance of out or around out. So we try to estimate the Coulomb's force between these two protons. Okay, so this is pretty easy. Okay, you just need to plug in the values in the Coulomb's law. So F equals K times E squared over R squared. Okay. So Q1, Q2, both of them are protons. So the charge will be plus E. So E times E is E squared. And then the distance is R. So we just plug in all the numbers. 8.99 times 10 to the 9th power, and then times 1.6 times 10 to minus 19, and then all over 4 times 10 to minus 15. This is the radius, okay, and then quantity squared. Okay, so this force is quite large, which is 14 Newton. 14 Newton. Okay, so this is simple. Okay, we just move to the next part. So for part B, it asks you what is the magnitude of the gravitational force between those same two protons. Okay, so just now we know that there are some force repulsing, repelling the protons. Okay, of course both of the protons have a positive charge, so the force must be repelling. Okay, otherwise they should move according to Newton's second law of motion. Okay, but as you know, they can only oscillate nearby. Okay, so they can really move. Okay, so let's try to find whether any other force that are attracting them. Okay, and actually, as we have learned, there should be something called gravitational force in the mechanics. Okay, you know, I suppose you are familiar with it. So yeah, actually, in this course we won't use this gravitational force later on. So we just need this to tell the story of these 2 pages. Okay, so this is the gravitational force between two objects. Okay, MP is the mass of the proton, and then R is actually the same distance between the 2 protons. Okay, so this is the gravitational force, and we just need to plug in the number 6.67 times 10 to minus 11, and then times the mass of a proton is 1.6 times 10 to minus 27, and then over 4 times 10 to minus 15, and then quantity square. So the value is 1.2 times 10 to minus 35 Newton. Okay, so this is really small compared with the previous one. This is 14. This is 1.2 times 10 to minus 35. So it is more than 36 order difference. Okay. So yeah. So up till now, the story is that, of course, we know there are something called the electromagnetic force. This is so-called the electromagnetic force. Electromagnetic. Of course, this is only electrostatic force, but in the physics, they only separate the force into 4 types. One of it is electromagnetic force. Of course, it includes F equals QE, F equals QE, and then plus QVB. Okay, maybe in high school physics you already know this QVB, or if I write it in a vector form, it should be like QE plus V cross B. Okay. So it's also called the Lorentz force. Okay, but actually in physics, we only call the whole thing the electromagnetic force. So electrostatic force can be also included as the electromagnetic force. Okay, so this is okay, so usually the magnitude of the electromagnetic force is medium. It's medium. It's medium. Okay, so there are four types of forces in the universe. Four types of force. The first one is the electromagnetic. You already know. The second one is the gravitational force. Gravitational force. Gravitational force, which is this one. This is the gravitational force. Okay, so this is very weak compared with the electromagnetic. Yeah, of course we know some gravitational force can be quite large, but it needs a very large mass, just like yeah, the mass of the Earth. Okay, the gravitational force between us and the Earth. Okay, so you know the mass of the Earth is very large, so this force can be strong, but yeah here when we consider this thing for the two protons, yeah, the gravitational force for the two protons and the electromagnetic force of the two protons. Okay, you can imagine this this electromagnetic force is much stronger than the gravitational force. And two other force, one is called the weak force, one is called the strong force. Okay, of course, even in this course we won't learn what it really is. I can only tell you something like, oh, this is something like the weak force is something like the fission and fusion. Fission and fusion, like fission and fusion. Okay, in Chinese it's called 核裂变、核聚变，就是核能那些，就是 alpha decay, beta decay 那些。Okay, it's so called the weak force. Of course, it is also strong. It's even it is called weak force, it is strong. You know, when you really need the nuclear bomb or nuclear plant for the electricity. Yeah, it can generate lots of electricity. Yeah, but also although it's called weak force. Another type of force is called the strong force. The strong force. The strong force is the force which is acting between the nuclear. So just now we already know that there are strong force repelling the proton, and then there are only weak gravitational force to attract them. So there must be some other force to force this nuclear to be stable. Otherwise, it will just explode, because yeah, there are strong repelling force. So there are some force that is acting between the particle. Of course, we won't really know try to go deep into this talk. Yeah, this topic. Yeah, just let you know a bit about there is something called a standard model of elementary particles. 粒子标准模型。So it tells you there are some so-called elementary particle. Okay, so in high school chemistry, we only know some fundamental particle called proton, neutron, and electron. Okay, so in this table, we can still find the electron. So electron cannot further separate into smaller one. Just why the elementary charge is 1.6 times 10 to minus 19 Coulomb, not as even smaller value. You cannot even separate a charge. So even though the text is quite small, you can see, oh, this is mass, this is charge, this is spin. Okay, in high school chemistry, as you should know, the spin for the electron is like plus or minus one half. And this and you can see on the left part of this table, there is so-called the fermions, 费米子. 非离子. Okay, fermion. The fermion will have a spin of 1/2. Okay, you can see 1/2. All of them are 1/2. 1/2. These are so-called fermion. And then on the right-hand side, we can see the boson. For the boson, the spin will be 1. Okay. If you want to ask what is boson, actually I don't know. But yeah, actually, you can see the charge of the electron is -1. And in this table, you cannot find proton and neutron. You cannot find them in this table, which means that you can even separate the proton and neutron into even smaller fundamental building blocks. Just like when you play the Lego, you have some fundamental building block. Based on this building block, you can just build it into a house, into a whatever, a car or whatever. Okay, so in the world, we also have some elementary particle, just like the fundamental building block in the Lego. Okay, so actually, for a proton, if I remember correctly, it is like 2 up plus 1 down. Okay, so you can see here for the purple color, you can see this is quark. Quark. In Chinese, called quark. Okay. On the right side, we also have the Chinese Chinese name. Okay, so yes, the purple one, it is called quark. Of course, there are three generations. For different generation, you need different energy to generate them. So you can see the max is 2.2 mega, 4.7 mega. And then here you can see 1.28 giga, 96 mega. And then for the third generation, it is even larger, 173 giga, and then 4.1 giga. You may ask whether we can find even larger, maybe for the fourth generation, but up till now we cannot find that, because we need something called particle accelerator or particle collision device to do that, like 粒子加速器或者是那些什么粒子对撞机才能你要有足够的能量才能产生那么相对应的能量的夸克。Okay, so we need more energy to generate the higher generation of the quarks. So at least for the proton, it is formed with 2 up and 1 down, and then for the neutron, it is formed with 1 up and 2 down. Actually, you don't need to remember. Just tell you some hardcore physics story only. Okay, so you can see if you try to add up this 2/3, and then with -1/3. Okay, so if I just have a 2 up, which means 2 times. This is 2 times 2/3 plus 1 times -1/3. This is a down. This is the up. If we have 2 up, 1 down, it will have a plus 1 elementary charge. So it's a proton. So for the neutron, if we have 1 up and 2 down, so it will be 2/3 plus 2 times -1/3. So it is 0. So the physician try to build up this so-called standard model of elementary particle to see whether it meets our observation. It meets the observation. It meets the experiments. Okay, so up till now it's like this. So you know, on the bottom, on the top left, it is a quark. For the bottom left, it is called the leptons. 氢子. Okay, so it's very light. Okay, so you know the electron is very light. It is hundreds of times lighter than the protons and neutron. You know, the protons is 1.6. This is the mass of the proton. For the mass of the electron is 9.11 times 10 to minus 31 kilogram. Okay, so it's quite a bit lighter. Okay, so this is called leptons. Leptons. And on the right side, we have something called of course, we have something called the boson. Bosons, Weifan bosons. Okay, so yeah, in the nuclear we have something called the gluon. The gluon, 胶子 gluon. So it's like the glue, 就像胶水那样，就把那个 so the gluon try to glue the nuclear together because it has strong repelling force. So the gluon it's like the 胶水那样。So it try to collect all the protons and neutrons together. Of course, there will be some strong force between them, so to make the nucleus stable. And also you can see photon. Photon. Maybe you already know this term. And on the very right, we have the Higgs boson. Higgs boson. So several years ago, yeah, we know that. So this is called the 上帝粒子. 上帝粒子. If you yeah, just read some science news about science news about about the very advanced physics in several years ago. So the physician have find the Higgs boson. Okay, the Higgs boson is it's very stressful. It's just like you can you should imagine like for the mass of something it has its own mass. But actually the Higgs boson try to separate, try to allocate the mass to different particles. So it's very, it is very strange thing. So the physician try to call it 上帝粒子. Okay, in Chinese it's like 就是平常你会觉得就是一个粒子有多少质量的话，就是它自己的事情。但是其实的话是，那个 Higgs boson 就是会跟其他的粒子有相互的反应。那相互反应的结果就是它会分配一些质量给一些其他的粒子，所以它就像一个上帝的存在，就是我给你一些质量那样。Okay, so this is very difficult and hard to imagine things. But yeah, just let you know some hardcore physics. You actually we won't have tests about that. Just let you know the physics story. Okay, so the next topic is called charges conserved. 电荷守恒. Okay, so which means that we cannot create, we cannot diminish the charge. Okay, just like here we have a reaction formula. Like if we have a so-called electron, this is a normal electron, and this is called a positron. Positron. In Chinese it's called 正电子. 正电子. Okay, if so they are so-called antimatter 反物质. 互为正电子跟电子就互为反物质 antimatter. Okay, so when the antimatters pair interact with each other, they will all vanish, and then they will change to some energy. Okay, so because even though the electrons are very light, there are some mass. And if true, yeah, of course the charge is conserved. So on the right side, we won't have any charge. We won't have any charge. But at least before the reaction, there are some mass. There are some mass. And later on, it turns out to be some light, some energy. This is called the gamma ray. The gamma ray. The gamma ray is a type of electromagnetic wave, 电磁波. So it only have energy but no mass. Okay, but on the left side there are some mass. Oh, how come it would be like that? So in the relativity 相对论狭义相对论 we know that E equals mc squared. E equals mc squared or something like E0 plus mc squared. Yeah, I'm not sure. So should be something like that. Okay, so on the left side there are some mass. So after the reaction, it will all change to energy. So it depends on how large the mass is, and then this is the speed of light. This is the speed of light. And then all the mass will change to energy. Okay, on the right side. Okay. Or the other way around, if we have strong energy, it may be able to generate the pair of electron and positron. Actually, in the Earth, we also can have some positron. When there are lightning, 闪电. When there are lightning, it may generate some positron. Okay, this is a natural phenomenon. We don't really need to create this condition by ourselves. It just happened in the Earth. Okay, so there are some complicated formula, but just let you know that we cannot create the charge. We cannot diminish the charge. So on the left side, on the right side, the total charge amount remains the same. So it's called the charge is conserved or conservation of charge. 电荷守恒. Okay, so just now I mentioned something called gamma ray. So here just slightly see, this is so-called the electromagnetic spectrum. We will go back at chapter 33. So here, just let you know a bit about it. Okay, so here, there are three axes. So, but actually, it's not that difficult. The two main axes you need to pay attention is first the frequency, and the other one is the wavelength. And on this whole page, it is so-called the electromagnetic wave, 电磁波. Okay, so the wave speed of the electromagnetic wave is always c equals 3 times 10 to the 8 meter per second in vacuum or in the air. Okay, so another equation you may have learned is so-called C equals F lambda. So F is the frequency, lambda is the wavelength. So this is lambda, this is F. Okay, so on the so for the frequency axis, this is large, and another formula related to it is like E equals HF or H nu. Maybe some physics textbook it will use H nu, but generally I'll use HF. Okay, so H is so-called the Planck constant. The Planck constant. F is the frequency, and E is the energy of a photon. Energy of a photon, which means that this is a constant. If F is higher, the energy of a photon is also higher. So here on this axis F, this is large. So you can see the gamma ray has the highest energy between the when you try to count the energy of a photon. So the gamma ray should have the highest energy. Okay, and then for lower we have something called X-ray. Yeah, when you need to do the body check to enter the university, then you may need to use the X-ray to see whether your lung is healthy. Okay, so like X-ray, it is slightly weaker than the gamma ray, and then here we have we can see the visible light, 可见光. And then for even slightly high energy, it is ultraviolet, 紫外线, and then this side infrared is 红外线. And then for even lower frequency, we have microwave and then radio wave. So you can see somewhere here. So we use this range of frequency for the wireless communication. Okay, so for example, for the Wi-Fi, you generally use the 2.45 gigahertz band or 5 gigahertz band, something like that for the Wi-Fi. And then for 3G, 4G, or even 5G, they will use the frequency around 800 megahertz up to 3 gigahertz, around that level. Not a very precise value, but around that range. We will use it for wireless communication. And yeah, even for GPS, this is using 1.5 gigahertz, so on and so forth. So around that level, we try to use it for different kind of wireless communication. And for 5G, it is different from this 5 gigahertz. Okay, it means the 5th generation of communication. 第5代的流动通讯. Also, it generally use 28 gigahertz. So it is a bit higher. It is around here for the 5G. Okay, so you can see this is around the millimeter wave level, so-called the millimeter wave level. So of course, so you can see here, F and lambda is inversely proportional to each other, which means that if it has a higher frequency, it should have a lower wavelength. So which means that for gamma ray, the wavelength is very, very short, 10 to minus 12 meter. And here, for the 5G, if it uses 28 gigahertz or even higher frequency, it is around the level of a millimeter wave. So we will somehow call it the millimeter wave. It is around that level. Okay, so for even lower frequency, we need so the wavelength is longer and longer. So we need a larger and larger antenna to receive the signal. Just like if you listen to the Macau radio station, it is 100.7 megahertz. 127 is around here. So yeah, you can see the wavelength is around 1 meter, around 1 meter. So when I was small, the radio is like this is a radio, and then with a very big antenna to really receive those signals, because the wavelength is large. So you also need a long antenna to receive those kind of signals. And if you really need to use your mobile phone to receive the FM signal in the air rather than from the internet, then you usually need to plug in your headphone. So your headphone is quite long with the wire. So it acts as the antenna to receive the FM signal. So of course, if you just receive the Wi-Fi signal to listen to the radio or whatever, then the other story. But if you really need to receive the FM signal in the air, then you need a long antenna to do so. Okay, so this is just a simple story. Okay. Yeah. So yeah, maybe we just skip this one. I don't think I need to do this one. I just skip this. So we still have a additional problem to finish off this chapter. So let's see. Yeah. Okay. So here, yeah. So here, it says three identical conducting sphere. Three identical conducting sphere initially have the following charges. Okay. Sphere A 4Q. So sphere A have 4Q, and then sphere B have negative 6Q, and then sphere C 0. Okay, sphere A and B are fixed in place and with the center-to-center separation that is much larger than the sphere. Okay, so which means that you just ignore the force between them. Ignore the force between them. Yeah. So So here we have two experiments are conducted. So experiment 1. So we try to touch C with A, and then separate C to sphere B, which means C touch B later. Okay, and then it is removed. So let's and then for the experiment 2, starting with the same initial state, the procedure is reversed. So C touch B first and then touch A. Okay. So it asks you what is the ratio of electrostatic force between A and B at the end of experiment 2 to experiment 1. Okay. So let's try to do this. Okay. So here is like let's try to write A, B, and C. And then first we consider the experiment 1. And at the very beginning, A has a 4Q, and then B has negative 6Q, and then C has 0. This is the initial setup. Okay, so for the first step, C touch A first. C touch A. C touch A, which means that these two numbers add together and then divide by 2, and then equally separate to A and C. Which means that 4Q plus 0 is 4Q, and then divide by 2 is 2Q. So 2Q, 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 okay, 0, 4Q. Okay, and then B remain unchanged, negative 6Q for the first step. And then for the second step, C touch B. So here we have a C and B touch each other. So A remains unchanged, it is still 2Q. And then for BC, negative 6Q plus 2Q add together to be negative 4Q, and then equally distribute negative 2Q, negative 2Q. Okay, so this is the final state for experiment 1. Okay, and then for experiment 2, for the initially, it is still negative 4Q, plus 4Q, negative 6Q, 0. And then here, we first do C and B touch each other. C and B touch each other. So A doesn't change 4Q. And then for BC, negative 6Q plus 0 is negative 6Q. And then divide by 2 is negative 3Q. So this is negative 3Q, negative 3Q. Okay, so for the next step, C touch A. C touch A. Okay, so C touch A, so which means that B doesn't change. And then A touch C. 4Q plus negative 3Q is Q. So divide by 2 is FQ. Q over 2. Okay, so finally, we will try to calculate F2 over F1. F2 means for the experiment 2 between sphere A and B. Okay, so here we have for the F2 between A and B will be K times Q over 2 times negative VQ. And actually we don't need to consider about the polarity, because we only consider the ratio of the force magnitude, the magnitude. So we just consider 3Q is okay. And then the distance between A and B is D, so D squared, and then it doesn't change. So finally, it will just cancel. We don't need to know what D is. Okay, for experiment 1, 2Q and negative 2Q. So we have a 2Q times 2Q over D squared. Okay, so finally, many of them can be cancelled. K and K can be cancelled. D squared and D squared can be cancelled. Q can all be cancelled. Sorry, Q rather than 2. Q. Okay, so finally we have 3 over 2 over 4. 3 over 2 over 4. 3 over 2 all over 4. So this is 3 over 8, or 0.375. Okay, so this is the answer to this question. Okay, so so we finish off this chapter, and let's have a 10 minutes break. We will resume class at